jet engine model RC.
So here we go. Whew. Finally getting started here. So this next unit, like I said, it's a little bit more conceptual, and it's got two theorems we're going to be learning, and they are named theorems, which means these are theorems you're going to want to write down on an index card and, like, flashcard yourself to make sure you get them down. So the big ones so far are the extreme value theorem, right, in this unit, and then we're going to talk now about Rolle's theorem and mean value theorem as well. Okay, so two named theorems. We're going to stick on Rolle's theorem first. I don't know. It's a good question. He could be French, though. He could be French. So for this, we're going to label the points 1, 3, and 5, 3 using this graph down here. And then I want you to draw a graph of a differentiable function that starts at 1, 3 and ends at 5, 3. Okay, so first of all, let's remember, what does it mean that the function must be differentiable? How will that show up visually in your little sketches?
Well, it can't be pointy.
No pointy parts. Right, no open dots, got to be continuous. So it's no points and it's got to be continuous. Yeah, the breaks would also cover like under continuity. So right, that means no points and continuous as well. Okay, so that's what it's going to look like. So then I would like you then at this point, so I just wanted to cover that first because these other two questions are going to be for like after you've drawn the graph. So I want you to use this little space down here. How can we do that? Well, you're going to put little tick marks here. So like 1, 2, 3, 4, 5, so on and so forth. And then 1, 2, 3. All right, so we're going to start at the point 1, 3. And then at 5, 3 as well. And then, like I said, I want you guys to go ahead, draw a graph of a differentiable function that starts at that point, ends at that point, okay, and then answer those two bulleted questions there. Okay, or think about those two bulleted questions if you don't want to answer them.
Like,
all right?
That's the range.
So what I want you guys to do is to, draw a graph, basically connect the dots from this point to this point, but make sure your function is differentiable that you're drawing. Sketching, really, is all you got to do. Yep. Did I do 6, 3?
Do they have to be?
Whoops. Thank you.
Do they have to be differentiable at the endpoint?
Well, no. Not on the endpoints.
Could we not just draw a straight line?
Could you draw a straight line? Sure, if you want to. But I mean,
you want to fail this class?
Right, you want to fail? No, I'm just kidding. So again, draw your little differentiable function. Christian's looks good. Caleb's looks good. Ryan's okay, looks good. Yeah, that works. Yeah.
You should not have said that.
Okay, good. That's good. Okay, yeah. Tyler's still trying to think about it.
Tyler's like,
It's all zero. It's all zero. It is literally all zero.
Connor's like, I don't know how to draw. I don't know how to.
Good.
Connor's like, what is pencil?
That works.
Left on.
Okay, so I see a lot of good differentiable functions. Now go ahead, in that first bullet, is there at least one point on the graph for which the derivative is 0?
Yes. Sure. 3.
Don't know? Why don't you know? If you have a horizontal line, right, your slope is going to be 0 everywhere, okay, right? And if you look at some other ones, so if I may borrow yours here real quick, Caleb, since yours is handy. All right, so Caleb drew that. Does it look like the derivative will be 0 at least one place in this piece? Yes. Okay, let's look at Christian's here too. He drew a little more complicated thing as well, but this works. So does it look like Christian's will have at least one point on the graph where the derivative is 0? Yeah, it looks like in fact 2, possibly 3, but probably 2 for sure. 2 for sure, okay? So that's right. So the answer is yes, right? Yes. Would it be possible to draw the graph so that there isn't a point for which the derivative is 0? Explain your reasoning. So what I mean is, following these same conditions, keeping the fact that 1, 3, and 5, 3 are going to be our endpoints, all right, and we want it to be differentiable. Is it possible to draw such a graph so that there won't be a place where the derivative is 0?
I'm going to say no, there's no space to draw.
Right. So what? No open circles. Yeah, because remember, to be differentiable, it has to be continuous, therefore. And so yeah, Emma? So, good question. Would that then, that would not fit our requirement of being differentiable because we have a point. So the answer here is that it is not, because if we go up, what do we have to do? We have to go back down. And if we go down, we got to go back up. And if we go up and down, we have to go back up. You know, any sort of combination there, okay? And so when we go up or down to up, we end up with these horizontal tangents. Okay, that's right. Okay, so there it is, yin-yang. All right.
Physics.
So the idea is that we would have to either go, we would have to then create a place where it equals 0. And so this, what you guys basically just saw here, is what we call Rolle's theorem. Okay, so here it is, Rolle's theorem. We're going to fill this in here. So let f be continuous, okay, on the closed interval A, B. Oops, not a period. And, so let f be continuous on the closed interval A, B, and differentiable okay, on the open interval A, B. So again, like the situation we had just prior to this, right? Our function was differentiable at everywhere but the endpoints, and it was our function was continuous on the closed interval. So that's what we just had, right? That was where the things we abided by. So if f of A equals f of B, was that the case in our previous example here? Did f of our left endpoint equal f of our right endpoint? Yeah, they were both 3, right? It was the point 1, 3, and 5, 3, so that f of 1 was 3, f of 5 was 3. So the endpoints both have the same y value, right? They were both the same height. So if f of A equals f of B, then there exists at least one number C in the interval A to B, the open interval A to B, such that f prime of C equals, well, what do you think we can guarantee here from the activity we just did? Right, such that the derivative must equal 0. Okay, here is a visual representation right here of Rolle's theorem. Okay, if you look here, it's very generic, right? But here's A, our left endpoint, here's B. Is f continuous? Is f differentiable on the open interval?
Yes.
So yeah, so f continuous on AB, f differentiable on AB. So like check, check. What's the other condition? F of A has to equal f of B. What does it look like? F of A is the same value as f of B? Basically, right? I know it's a sketch there, so we kind of have to like see that. But it looks like this is, okay, f of A equals f of B, so check. So there must be some C value. Notice here, in the theorem, does it tell you where that C value, what the exact C value is? No, it just tells us where the C value is. It's going to be between A and B. But we are not told that there must be, or that we're not told, sorry, we're told that there must be a C. We're not told what value that C must be, though. We're not told what C is going to equal. We know C is between A and B, and we actually are told there could be more than one place, right? So we're told there exists at least one number C in AB such that f prime of C equals 0. Now looking at the picture here, there's only one place where between the interval A and B, there's where the derivative equals 0, and that's right there. Okay, so there's only one, but there could be more than one, right? We saw with Christian's example, there could be more than one. Okay. So, that being said, so Rolle's theorem holds true right here. Rolle's theorem is true here. There's where f prime of c equals 0, right there. That's that c value. Okay? Now, let's look over here at this second example. Will Rolle's theorem hold here? Okay, so why does Rolle's theorem fail here? The function is not differentiable. Is the function continuous? Yes. Pointy parts are okay. So f is continuous on the interval closed interval AB. F, so that's true. F is not differentiable. Rolle's theorem does not apply. Okay. Could the derivative still equal 0? Well, not in this case. But yes, the derivative still could equal 0 at some point. Okay, so just because Rolle's theorem fails does not mean the derivative then therefore never equals 0. No, that's not what Rolle's theorem says. Rolle's theorem says if these conditions are true, if f is continuous on the closed interval, if f is differentiable on the open interval, if f of a equals f of b, that means f at the one endpoint is the same as f at the other endpoint, then, and only then, can we guarantee at least one number c in AB such that f prime of c equals 0. Okay? That's it. If this fails, the derivative still could equal 0 at some point in that interval, but it is not guaranteed to. Rolle's theorem merely guarantees the derivative must equal 0 if these conditions are met. If f is continuous, if f is differentiable, and if f of a equals f of b. Okay? That's what guarantees then that the derivative equals 0. All right? Questions on any of that? So that's Rolle's theorem. 3 conditions. F continuous on the interval, f differentiable on the open interval, and then f of a equals f of b. If that's true, those 3 conditions, then f prime of c equals 0. Okay? So, let's go to the back. Okay, so the back has us determining whether the function f of x equals sine of x over 0 to 2 pi satisfies the conditions of Rolle's theorem. If f does, then find the guaranteed points. Because remember, Rolle's theorem does not tell you where the derivative equals 0, it just tells you that the derivative must equal 0 at some point in the interval. So let's first of all check. All right, first condition we have to check. Actually, first thing, let's graph this. Let's do that. Okay, so we're going to graph it from 0 to 2 pi, so we'll start at 0. And sine of 0 is 0, that's right, okay. And we'll go out to pi, and then out to 2 pi there. And then we have to do our halfway point, so pi over 2, 3 pi over 2 to get the really good points in there. Okay. Sine of pi over 2 is 1. Sine of pi is 0. Sine of 3 pi over 2, negative 1. Sine of 2 pi, 0. Okay, so there's the graph. Alright, so what's our first condition for Rolle's theorem? Is f continuous? Now we only need to check if f is continuous on the interval. If f is discontinuous, but it's outside the interval, doesn't matter. We only care if f is continuous on 0 to 2 pi. So is it? Yes. Okay. 2. Is f differentiable? Whoops. For the open interval 0 to 2 pi. Is f differentiable on this interval? Yes! What are we looking for visually to determine that? Holes and points, right? Discontinuities, but we already know it's continuous, and so for differentiability, then just pointy parts, and so there's no points, so yes, differentiable. And then finally, step 3, does f of a equal f of b? Yeah, what is f of, well, a in this case is 0, f of 0 is 0, b in this case is 2 pi, f of b, f of 2 pi is 0. So yes, f of 0 equals 0, which is equal to f of 2 pi. So yes. So Rolle's theorem applies. So therefore, because these 3 things are all yeses, that means we know what must be true. Yes, there must be one point in what interval from 0 to 2 pi such that the derivative equals 0. In fact, in this case, there are 2, but the Rolle's theorem just says there must be at least one, so that still covers 2. Right? So we can say, all right, f prime of x, and let's actually find them. So we'll just set the derivative equal to 0 then. So, all right, derivative of sine is cosine, and so we set that equal to 0. Now you might wonder to yourself, Mr. Widmeyer, why the heck do we do all this 1, 2, and 3 here? Why we graph it if all we're going to do is just take the derivative and set it equal to 0? Well, because this is how we practice with Rolle's theorem, okay? There will be other situations where you won't be able to take the derivative and show that it equals 0, right? Right now, we know when cosine of x equals 0. When does cosine x equal 0?
Pi over 2
At
and 3 pi over 2.
At pi over 2 and 3 pi over 2, right? If you don't, like, you know, you can also just look at the graph right here, right? Tangent line, tangent line. So there's where the derivative equals 0. Pi over 2, 3 pi over 2, okay? But we won't always have a function that we can take the derivative of, okay? But we can still identify whether it's continuous and differentiable, and therefore guarantee that it will be equal to 0 at some point. The derivative will equal 0 at some point. Okay. Questions on anything thus far? Questions, questions, questions. All right. So let's go ahead and take a look at these then. All right. So letter A. Find the 2 zeros of the function. Find the 2 zeros of the function and determine whether Rolle's theorem can be applied on the interval of the zeros. So we're gonna. Wow, look at that. Zeros spelled 2 different ways there. I think both are acceptable. I'm not sure about that though. All right, I know, right? This is math class, not English class, but anyway. If Rolle's theorem can be applied, find the values of c such that f prime of c equals 0. Okay, so we got to find the zeros first. So let's see here. I'll say 0 equals x minus 3 times x plus 1 quantity cubed. Right, to find the 0, squared, sorry, it's a squared. Right, to find the zeros, that's just finding when the function equals 0. So there they are. So what are the zeros here then?
3.
Yeah, 3 and
Negative 1.
-1. So that our interval is not going to go from 3 to -1, right? That's the wrong direction. We're going to go from -1 to 3. So our interval for this function is from -1 to 3. So is f continuous from -1 to 3?
Wait, shouldn't we figure out if -1 and 3 equal each other first? Like, I feel like that'd be the easiest one.
Okay, so good question. Good question. We already know that -1, f of -1 and f of 3.
Oh, because of equal 0.
Because how did we get them in the first place? We got them by setting our function f is equal to 0. So since they're both zeros, they'll both be on the x-axis.
Okay.
And that's why we did it that way. No, that's good that you thought that way. I mean, yes, we do need to check that. But because we calculated them, because they're zeros, they're going to be the same height. So, is our function continuous from -1 to 3? You might wonder, but how are you supposed to determine that? There's no graph now, Mr. Widmeyer. How are you supposed to know whether this function is continuous from -1 to 3? Well, we could graph it in our graphing calculator, but we can actually just look at it. Yeah, there's no like discontinuities or anything, right? You can plug in any number between -1 and 3, and you're not going to get anything that's dividing by 0 or anything like no jumps or anything like that. It's not piecewise. So I mean, yes, we can assume from all that it's going to be continuous. All right, is f differentiable from the open interval? Open interval from -1 to 3. That's a bit trickier, isn't it? To look at differentiability, we again need to look at the graph of this to see if there's any pointy parts, or what else can we look at? Continuity of the derivative. That's right. So we can look at the derivative and see if the derivative would ever be discontinuous. That would also help us determine differentiability. So let's take the derivative. Oh man, the derivative here is going to require us to use a product rule. so much fun. Okay, so I'm going to pick some lucky duck here to help us. Joey. Lucky duck.
So,
What's going to be the derivative here?
we got x minus 3
Uh-huh.
times
Times 2.
times x plus 1,
Uh-huh.
and that would be times 1.
Times 1, so, okay. Uh-huh.
Then we'll do plus x plus 1 squared,
Uh-huh.
and then times 1.
Times 1, so I'll just leave it like that. Okay. Very good, Joey. Well done. Okay. So let's taking a quick look at this. Will f be differentiable on the interval from -1 to 3? Yeah. Do we see any problem areas for any of the numbers between -1 and 3? No. There's no dividing by 0. There's no jumps or gaps or anything like that. It's just, we're just going to plug numbers in and get some numbers, okay? Get some values. So, yeah, this is differentiable from -1 to 3. Faux show. Okay. And of course, Ryan wants us to check this. F of -1 is equal to 0. F of 3 is also equal to 0. So, F of A equals F of B. So we hit all three of our conditions. 1, 2, 3 conditions for Rolle's theorem. Rolle's theorem applies. So since F is continuous on -1, 3, and F is differentiable on the open interval -1 to 3, and F of A equals F of B, then we can say that what must be true? The derivative must equal 0 in this interval. There must be some x value between -1 and 3 such that the derivative equals 0. And the directions ask us to find that c value such that we can say when the derivative equals 0. So that means, what do we still have to do then? Set the derivative equal to 0 and solve. Okay? Any ideas here for us? Yes, does everyone see this? Very important here. We did a product rule, and there is, I told you guys, when you're doing those product rules, keep an eye out for GCF. There is a GCF here of x plus 1 that we can factor out. Believe it or not, that will help. So I factor out x plus 1, I'm left with x minus 3 quantity squared plus x plus 1. Thank you. Oh, I did, you're right. Sorry, it's a 2 times quantity x minus 3. Mr. Wid. Look at that. That's bad handwriting right there, guys. Sorry. Okay. So it's x plus 1 times 2 x minus 3 plus then x plus 1. Okay, like that. We're all good with that? I didn't confuse anybody and lose anyone with that mistake that I just made there? We're all good from here to here? Okay. So then we can just distribute. This is so much easier than multiplying all that stuff out. It becomes 2x minus 6 plus x plus 1. And so we get 0 equals x plus 1 times, let's see here, 3x minus 5. And now you can split it up, right? X plus 1 equals 0, 3x minus 5 equals 0. So x equals -1, and x equals 5/3. So there are actually two places here that Rolle's theorem guarantees, right? But we throw out the -1 because it's the end point, okay? It's an end point of our interval there, and we don't include the end point. It's got to be in between A and the B, so only the x equals 5/3 is the solution. Okay? That's a little tricky, that's right.
On a quiz test, they put x equals -1 and then that points to the
Possibly.
Because
So
I
be
feel
careful
like
with that,
that's one
guys.
of those things that, like, it could be that if you include it, you can't go wrong. So you just include everything you get.
Right.
But then it also doesn't apply to Rolle's theorem.
Yeah, that's not the. This is the only value guaranteed by Rolle's theorem. This one's not. I know it's a bit tricky. I don't think I trick you guys. I don't think there's going to be something like on the test where you'll be like, this multiple choice answer has -1 and 5/3. This multiple choice only has 5/3. I don't think I do something like that. That's too tricky. You're like, Mr. Whitmire, some of the other stuff you do is too tricky. All right, I understand. Anywho, last one here. Let's get this one done. Sorry. So again, going through this, we've got this f of x equals x to the 2/3 minus 4. So again, we want to check. We want to find the zeros, sorry. So we'll set that equal to 0. Okay, find the zeros. Add 4 to both sides, right? Believe it or not, we can do this without a calculator. To get rid of x to the 2/3, what do we raise each side to the power of? Yeah, to the reciprocal power. So we'll raise 4 to the 3/2. We'll raise 2/3 to the 3/2. Okay? X to the 2/3 to the 3/2 becomes just what? X. 4 to the 3/2 is 8. Yeah, you can either cube 4 and then take the square root of that, which is kind of a big number, or you take the square root of 4, 2, cube it, 8. Okay? Cubing 4 gives you 64, square root of that is 8 as well, so you get the same answer either way. Okay? Wait a minute though, that's only 1, 0. We need another one to find, to have an interval here.
Would it be plus or minus?
It's plus or minus, that's right. It's plus or minus, because yeah, we did the square root technically there when we did the divide by the over 2 thing. So yeah, it's really plus or minus 8.
Does it matter that you're, like, you have to take the square root and then you also have to take...
Use a cube it or whatever. No, because when you cube something, the positive, negative stay negative, so it's still, yeah. Alright, so is f continuous? Is f continuous on the interval from -8 to 8 then?
I think so, yeah.
Can I plug in any number here and take the cube root of it and then square it and then subtract 4?
Yes.
Yeah, cube root of anything, you're fine, so yep. Is f differentiable? Well, we'll have to look at the derivative here. Okay, so let's go to Anna. So the derivative of x to the 2/3 minus 4, Anna, f prime of x. 2/3 x to the negative 1/3. And that's it. And that's it, right? Because minus 4 is just 0, so that's it. So it's 2 over, and then the x to the negative 1/3, Anna, where can we put that? In the denominator, that's right. So 3x to the 1/3. Okay? So, is f differentiable, Anna, on the interval from -8 to 8? Looking at our derivative there, Anna, can we plug in any number between -8 and 8 and be okay in this? So we have an x in the denominator, so what's something we got to look out for because we have an x in the denominator? So negatives, we can take the cube root of a negative, but what number don't we want in the denominator of a 0? Can x be 0? Is 0 between -8 and 8? Yeah, so x could be 0, and so is f differentiable for that entire interval? No. So cannot apply Rolle's theorem. Alright. So let's get our graphing calculators out and let's graph this to kind of convince ourselves, okay, what's going on here, making sure we were right. Okay, so graph that real quick. And just kind of convince yourselves that you're right. Remember, what does Rolle's theorem guarantee? That the derivative must equal what? 0 at some point in that interval. Okay, 0 at some point in that interval. Graph the actual function.
And now that equals 0.
My graph is having a hard time. Just taking a long time.
Mine doesn't look like that at all.
My graph.
Okay.
Oh, I got the derivative.
So there's the function itself. Now I'm only supposed to go, we're on the interval from -8 to 8, so if you want, you can adjust your window and only go from -8 to 8, so that way you're only looking at what you're supposed to look at. And what does it look like we have there at 0? It's pointy, that's right. And so there's no other horizontal tangents we can kind of see there. Compare that with the one from A. Oh my gosh, there we go. Compare that one with A, which when we graph that, and it's from -1 to 3. Let me adjust my window here. Okay. Sure enough, we have a horizontal tangent right there. Okay. and just at 5/3. All right? So there it is. Questions on Rolle's theorem. So again, I highly recommend you add, put that on an index card. All right, maybe even with the pictures there to kind of help you visualize and stuff. Remember, Rolle's theorem does not tell you where it equals 0, the derivative equals 0, just that the derivative must